Good morning, everybody. Welcome back after a long weekend. One announcement, we are going to have a midterm and it is going to be on March 3rd. It's a Wednesday. So on March 3rd, Wednesday. The format of the midterm is kind of like the homework. If you have been doing the homework, you're okay. My recommendation for you preparing for the midterm would be do the homework first and then do the lecture videos, watch the lecture videos or participate in the class. So that's what I would recommend. If you have been doing so, you are on track. You have nothing to worry. And midterm is going to be exactly like the homework. In terms of structure, only difference is that you will not see any step-by-step example or video examples if there are any. So you'll just see the questions and you'll be answering them. And as you answer, you'll see your score live. Okay, on the bottom right corner of the screen, you will see your score as you take the test. And I'll open the test at 6 a.m. in the morning, 6 o'clock in the morning. On the 3rd of March, and it will be available until 11:59 p.m. From 6 o'clock to 11:59 p.m., about 18 hours. Now, obviously, you don't need 18 hours. It will be like a couple of hours. Be prepared to work on the test for about 2 hours. And keep in mind that you can take the test for half an hour, work on it, stop and take a break and come back and work on it. So you don't have to take the test in one sitting. You can take it in multiple sittings and make sure to submit it. But if you submit it once, don't worry, you can submit as many times as you want. It's kind of like the homework. So if you by mistake submitted it once, no problem at all. Just submit it again. That should be fine. All right, that's about the midterm, the first midterm. And the second midterm, we are kind of planning on having it around the middle to after the middle of April. So after April 15th. After. Okay, so it'll be on the 3rd or 4th week of April, something like that. And of course, I'll give you the exact date as time gets closer. So nothing to worry, you will have plenty of time. So our first midterm will be 2 weeks from today, which is March 3rd. Okay, so let's go ahead and continue. Last time I did talk about probability. I have defined probability and defined some terms that go with probability. Define simple events, define sample space, and we use the concept of sample space and simple events to find probabilities associated with different scenarios. Okay, so I'll just do a quick review, since it's been a week since we had our last class. You had a long weekend, 4-day weekend, so you may have not been up to date. So let's go ahead and do a quick overview. I'm just going to do a quick overview of the things that I covered in the last class, and then we'll move on. So what is probability? Probability is the chance that some event or something will happen in simple, ordinary person's language. Okay, is the chance or likelihood that something or some event will happen. And how do we define probability? We define probability using the relative frequency definition. Number of times an event has happened divided by the total number of trials. Okay, the ratio of these two numbers is called the probability of event A. We define the probability of event A as number of times event A has happened and sub A divided by the total number of times you have tried. For instance, easy examples to remember. Tossing a coin. If you tossed a coin 1,000 times and you got 555 heads, that would be 555 divided by 1,000. If you tried 1,000,000 times and you got, let's say, 555,000 heads and divided by 1,000,000, that would be another example. So number of times some event happens divided by the total number of times you tried, or total number of trials. In the process, we have defined these terms, which you probably do remember. Events. So in this case, event A, like getting ahead, is an event. Simple event, an event that can happen in only one way, unique way of happening. There is no more, there are no more than, there is no more than one way of this event happening. Okay, so unique way of, or only one way of happening. Sample space is the collection of all the simple events. Sample space, it is the collection of all the simple events. What is a simple event? Easy thing to remember. If you toss a coin, you can get a head, right? That can happen in only one way. If you roll a die, the number 5 could show up only in one way. Okay, so that's a simple event. Collection of all the simple events is a sample space. When tossing a coin, what is your sample space? You can either get head or tail. That's your sample space. If you're rolling a die, what is your sample space? You can get 1, 2, 3, 4, 5, and 6. So that's your sample space. Okay, and each of these events are simple events because they can happen in only one way. Now, another way to think of something that is not a simple event, if you roll 2 dice, for example, how do you get the number 8? If outcome of those two dice, you add them up, and that's your event, particular event. So in our case, the event we are looking for is 8. So it's gonna be, you can get 2 plus 6 is 8, or 4 plus 4, 8, 3 plus 5, 8. So you could have one die 2, other die 6, one die 4, the other die 4, one die 3, other die 5. So this event, this outcome of 8 could happen in 3 different ways. That means it can happen in more than one way. Therefore, this is not a simple event. Not a simple event. Event that can happen in multiple ways. So that should take care of the basic definitions, and then we did some problems. Now, this problem, I got some questions. Anybody has any question on this? Couple wants to have 3 babies over the next 3 years. Create a sample space for the possible outcomes. And I kind of explained it in the last class that there are 2 possibilities only, boy or girl, nothing else, no twins or no other things, okay? And create a sample space. Here, of course, we said that the order matters, okay? Order matters. So the way we did it is boy, 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 girl, and we did all the way up to the last one. There are 8 possibilities. All right, and then based on this, we found these probabilities. Okay, any question on this one before I move on?
No.
Okay, so let's move on. Now, properties of probability, that's something important. Probability must always be between 0 and 1, or probability has to be between 0% and 100%. Probability must be between 0% and 100%, or equivalently 0% is 0 and 100% is what? 1. So probability must be between 0 and 1. You can think of probability as a function. So P of X, okay, it's a function. It takes a value X, okay. Let's say your X is the real number line, and it maps it to 0 and 1. That means your domain is the real number line, let's say, and your range has to be between 0 and 1, including the boundary points 0 and 1. So when I ask for probability, don't write something like 1.3. Okay, that tells me that you haven't followed the basics. Probability can never be bigger than 1 or can never be less than 0. So it is between 0 and 1. Probability of the sample space is 1. S is the sample space. Sample space is the collection of all the simple events or all the different things that could happen in an experiment. So probability of that happening, if you perform that experiment, must have to be 1. If A is the empty set we define, the probability of the empty set always 0. So probability of the empty set is always 0. This is phi, the Greek letter. If A is a collection of simple events, so if A is an event, which is a collection of bunch of simple events, A1 all the way up to AN, then probability of A is the same as the probability of A1 plus ... plus all the way up to probability of AN. That's what it is. That means individual probabilities could be added to get the total probability. If you have simple events, okay, collection of simple events, then the probability of all of them together is the sum of the individual probabilities. That's what it means. The probability that an event A will happen plus the probability that it will not happen is always 1. So probability of event A plus the probability of the A complement is always 1. When you are dealing with probabilities, an event either happens or it does not happen. It cannot be both or cannot be somewhere in between. If you are dealing with an event either can happen or it cannot happen. You either pass the class or you do not pass the class. You either show up for a meeting or you do not show up for a meeting. You either get this job or you do not get this job. So these are binary in nature. So remember, when we are dealing with probability, we're thinking of events as binary events. That means either it happens or it doesn't happen. There is nothing in between. So some of these probabilities must always add up to 1. Some of the probabilities must always add up to 1. Remember this rule. Probability of event A plus A complement, A prime, or sometimes some authors write it as A with a C on the top. A prime is equal to 1. Probability of A plus probability of A prime or A complement is always 1. Then we talked about these things, union, A, union B, that means items that are both in A, items that are in A or in B, okay, together. You combine them, but you do not write the items that are common in both of them multiple times. If an item appears both in A and in B, you do not write it twice, okay? So that's what it is. And A intersection B is a set that is including the items that are both in A and in B. A intersection B is a set that includes items that are both in A and in B. So this is and you can think of, and this is or. Okay, union goes with or and intersection goes with and that leads to the formula we talked about which is this: probability of A union B is equal to probability of A plus probability of B minus probability of A intersection B. And I have given you an example of this. This is probability of A. This is probability of B. Now, if you count probability of A, you're counting this area. If you count probability of B, you're counting this area. That means this middle region is being counted twice, once with probability of A, another time with probability of B. So you have to subtract it once. So that's why we say probability of A intersection B minus. So you subtract it. However, if these two events are disjoint, meaning A intersection B is the empty set, that means they don't look like this. They look like this. That means there is nothing common between them. So this is P of A. This is P of B, right? So then probability of A union B is going to be probability of A plus the probability of B. Okay. In that case, intersection becomes 0, right? This portion becomes 0. So you could say minus the probability of A intersection B, but this is what? 0, because this is the empty set. Remember, A intersection B, here there is nothing common between them. So A intersection B is the empty set. So the probability of the empty set is 0. So it really doesn't matter. So that's kind of in a nutshell what we talked about last time, and we have done some problems. And I told you that I'm going to be asking you questions like this in the midterm. So it's important for you to pay attention to this. This formula, we'll be using it. A intersection B, I mean A union B. And then we'll be doing problems involving A intersection B. And I will be asking you this question in the midterm, this coming midterm, and I will be asking you these questions in the final as well, so that you know what we are, what you're going to be expected. This is important stuff, probability, and you need to be able to understand the basics. And I can't emphasize enough about the importance of probability. Your entire life is probabilistic event. Okay, so far you have been thinking of math as a very deterministic thing, but the reality, the real world is probabilistic. The very existence of human life is a probabilistic event if you look at it from a scientific point of view. Okay, everything in life has a degree of uncertainty. Okay, you start your life with thinking you're going to have a long, happy life, and that is also a probabilistic event. That doesn't happen all the time, right? There are chances of that happening, then there are chances of not that happening. Like King of England, not king, prince, I guess, Queen's husband, he has had a long, happy life. I don't know if happy life, but long life for sure. He's 99 years old and he's at the hospital today. Hopefully he recovers. Okay, so events in life are probabilistic. That's something you have to get used to thinking. Everything has a randomness or uncertainty. Remember these two terms: randomness / uncertainty. There is randomness or uncertainty associated with it. Okay, now, as I told you, please don't work on this problem. Technically, we will work on it later if time permits. This conditional probability, by the way. And we talked about this problem where we use the set theoretic notation, A union B, A intersection B, then A, we find the following probabilities, right? And then we find the probability associated with A complement, probability associated with B complement, We find the probability associated with A complement union, B complement, these things, right? A complement union, B complement, and all of those things. And this is also another problem, this type of problem I will be asking you. Set theory is very important. I don't know if you guys know, some of you may know, fundamentally mathematics is nothing but set theory. Math starts with the set theory. That's the most fundamental thing, and at this level you probably don't realize it as much. The concept, the very basic concept of mathematics in and of itself actually comes from set theory, which is basically what I am describing here: union, intersection, those kind of things. But this is kind of like advanced mathematics. We don't talk about it at this level. Advanced mathematics, it involves with a collection of sets, union, intersection, or properties of sets with certain objects or certain mathematical structures. Anyway, that's a bit of an advanced topic. So let's go ahead and move on. And let's talk about conditional probability. I kind of like to give this example. Conditional probability is another very important topic. This is something that happens. People, you are using it in your life, yet many of you may not realize it. I'll give some examples that are very useful and practical. Easy to understand, and then I'll give you some examples which are politically incorrect. Okay, I shouldn't say politically incorrect. It's kind of is debatable, or at least some people would like to debate. But let's go ahead and start off with this very simple example. Let's say I personally watch a lot of basketball. I love watching basketball, and I watch NBA and sometimes the college basketball. Now, what is the probability that a randomly selected person, let's identify that person with X. Now remember, I have introduced the concept of variable X. It's a random variable, okay? Random variable. So let's say X represents a randomly selected person from the population. Probability of X, okay? X is the variable that's representing a randomly selected person from the population. Now, P of X represents the probability that a randomly selected person plays in the NBA. I'm making the example a bit more mathematical and harder, I guess. Let me just give you a non-math version of it first. That will help you understand things. So if you pick a person from the society, what are the chances that that person will play in the NBA? Probably pretty small, right? If you pick a random person from the society, the chances that the person will play in the NBA is pretty small. However, if I give you additional information where it says that the person you selected is over 6 feet 8 inches tall. The person you selected is over 6 feet 8 inches. Then the probability of that person playing in the NBA shoots up very high. The chances that the person plays in the NBA is much higher. If you're talking about the population of people that are 6 feet 8 inches or above, among them, the percentage of people who play in the NBA is much higher than it is in the ordinary population. So the probability that a randomly selected person plays in the NBA is very small. However, if I give you the additional condition that the person you selected or additional information that the person you selected is over 6 feet 8 inches tall, then the chances of that person playing in the NBA becomes much higher. So this is a very simple and easy way to understand conditional probability. Okay, very simple. Remember this example, you won't forget. Now, how do we express it in the mathematical structure? So probability of X, that means X is a randomly selected person from the population. So probability of by P of X, we define that the chance that the person that you selected plays in the NBA, which would be very small. I don't know, maybe one in a, there are 500 NBA players, by the way. So it's, you'd be surprised. Technically, your chances of playing in the NBA is 1 in 500,000. Okay, did I do it right? Yeah, I think I did it right. About 500 players in the NBA, in all the teams. So we have about roughly 270 million people, or let's say, make it nice number, 250 million people. Okay, so your chances of playing in the NBA is 1 in 500,000. So probability that the person plays in the NBA is 1 in 500,000. Now, the probability that the person you selected plays in the NBA, given that another event has happened, let's call it A, where A is the event that the person is over 6'8". Okay? A is the event that the person you selected is over 6 feet 8 inches tall. Now, if you give this, then this probability increases significantly. Then it might be even 1 in out of 100, I guess, or even less. Do you see? There's a sharp increase in probability. So that's the conditional probability. Conditional probability is very important, very, very important. Many things in life, real world problems are kind of modeled using conditional probability. So probability of event A given that B has happened. Okay, so given that something is given, so this vertical line tells you what is given. So A is the event that the person plays in the NBA. Okay, A is the, I should probably be a little bit careful about defining this variable X. X is a random variable that kind of tells you that you are selecting a person, okay, that plays basketball. You're sorry. Okay, so X is a randomly selected person who plays basketball or who plays in the NBA. So A is the event that a person plays in the, a randomly selected person plays in the NBA. B is the event that the person you selected is over 6 feet 8 inches tall. Now, probability of A is the event that the person plays in the NBA. Probability of event A is small, very, very small. Whereas probability of event A, given that you know additional information that the person is over 6 feet 8 inches tall, is kind of very high, I would say. So I have spent a lot of time talking about this, so I'm going to move on. So let's go ahead and give you another example. A is the event that a person has cold. B is the event that it is springtime. Okay. A is the event that a person has cold. So the probability of event A, that means the probability that the person has cold, there is a cold/flu. Okay. And that's probably some number. We don't know what it is. You randomly select a person from the population. What is the probability that the person has a cold or flu? Let's change the season. Spring. I meant to say something else. Cold. Winter. Okay, it's winter time. So this probability, and compare this probability with this probability of somebody having the cold or flu, given that it is winter, given that it is B. So that chance is probably much higher, because during the winter time, people have a lot of cold and flu, etc. So you can see that certain things becomes very influential in determining probability. Whereas if you do not have that information, the probability could be much smaller, or you don't have enough information to make very strong conclusion. And this may seem like something, I don't know how you're feeling, but I think this is very, very important, extremely important in many real world problems. I'll give you a couple of examples. One example could be your Gmail. Everyone's got a Gmail account, right? Now, if you look at the Gmail, you have inbox, right? Let me look at my Gmail. Give me a second. Let me see what do I have. Now, they have it as a primary. Then they have social, and then they have promotions category. Okay, this is basically junk mail that you don't want. This is something not quite junk, but social media type of thing. And this is your primary mailbox where you receive all the important mails. Now, how do you know which one is which? How does Google know this email should go to your primary, this email should go to your social, this email should go to the promotion category? I hope you're not thinking that Google has people who are sitting down and sorting it out for you. If that were the case, Google would be out of business in no time. If they had to do this, they would be out of business in no time, given that they don't charge for Gmail, I mean email. Right now, it's free, right? For this free service, if they had to have human beings sitting down doing this, this would be tremendously expensive. They won't be able to sustain, because billions and billions of emails going through Google every single day. So what do? They use conditional probability. They have programs where they use conditional probability. To be more precise, they use what we call artificial intelligence, or AI. They use AI algorithm that exploits this conditional probability, concept of conditional probability as well, and come up with these categories. So now here is here are two events. Let's define. A is the event, good email. Let's call it a good email. Okay. And B is the event that that it has certain words. Let's say sale. Okay. So what is the probability that the email you receive is a good email? That's what you need to know. Okay. It's hard to find out what that probability is going to be. It might be, it depends on what type of emails you receive, or it depends on, who your connections are, from whom you're receiving emails and whatnot. But in general, think of this. What if, in addition to finding out, getting the email, you have additional information that the email contains the word sale, or it contains the word like promotion. Let me take the back off. promotion, or it contains the words like offer. So if I say the following, this is one probability that an email you just received is a good email. That's what we are trying to find. That if it is a good email, it should go to your primary or inbox, okay? Now, given B, probability of A, given B means it contains the word sale, promotion, and offer, then you know that this probability is probably much higher. If the email contains the words in B, then there is a higher probability that this email is not a good email. Do you see how conditional probability helps you find the good email versus bad email? I'm just giving you sort of an overall idea, guys. There is a lot of mathematical modeling and data that goes into it. But big companies like Google, Microsoft, Amazon, or whoever out there, Apple, they have plenty of data, or Facebook, they have plenty of data to run their model and come up with a model that is going to identify good email versus bad email, or good conversation in case of Facebook, something important versus not important. So you can see how conditional probability can help you kind of resolve these kind of real world problems. All right, so any questions so far? I think I kept going on and on about the conditional probability. Anybody, any questions? No questions, everybody okay? All right. So how do you define conditional probability? To define conditional probability, I do the following. First, I define probability of A and B. Sometimes I'd write probability of A and B. Probability that event A will happen and B will happen. How do you define it? Okay. Easy way to define it is probability of event A times the probability of event B, given that event A has already happened. Okay. Given that event A has already happened. Probability of A intersection B, or probability of A and B, is probability of A times the probability of B, given that A has already happened. Or equivalently, it really doesn't matter which event happens first. Equivalently, you can define it as probability of event B times the probability of event A, given that B has already happened. Okay. Probability of event B times the probability of event A, given that B has already happened. Now look at the other one. If I define it this way, probability of event A times the probability of B, given that A has already happened. Both of these are equivalent definitions. So please use either of them. It really doesn't matter. Now let's bring back the screen. So there's A and B. Now I'm going to write it out here. Probability of A and B is equal to probability of B times the probability of A given B. I'm writing down this second one. Now I'm going to divide both sides of this equation by probability of B, assuming that probability of B is not 0. If I divide both sides by probability of B, what happens? These and these cancel out. That gives me this one. Let's write it out here. Probability of A given B is the same as the probability of A and B divided by probability of B. So this is the official definition. So probability of A given B is equal to probability of A and B divided by probability of B. So please remember this definition. This is one you want to remember, and there's another one that you want to remember. So this is the definition of probability of A and B, and this is the definition of probability of A given B. This vertical line is red, given. What is given? Probability of A given B. Any question, anybody, about the definition? Okay. Now let's move on. We define two events disjoint. Two events A and B are disjoint if the probability of A intersection B is equal to 0. Two events are disjoint if there is nothing common between them. So this is event A and this is event B. So let's call it A and let's call this B, right? Event A and event B. So if there is nothing common between them, what happens? You get A intersection B is equal to the empty set, right? Now probability of A intersection B is the same as the probability of the empty set. Now we know that the probability of the empty set is defined as 0. So probability of A intersection B is equal to 0. That is another way of showing that two events are disjoint. Sometimes we will also use the expression mutually exclusive. Okay. We say that two events are mutually exclusive. That means they can't happen at the same time. Two events are disjoint if the probability of the intersection is 0. And we have defined earlier that two events are disjoint if A intersection B is the empty set, right? Here we just extend it to another level. We just take the probability of both sides. And probability of the empty set we know is 0, right? So probability of A intersection B is equal to 0. Probability of A intersection B is equal to 0. That is another way of showing that two events are disjoint. Now let's go ahead and do this problem. Consider rolling a die. So this example. The outcomes are 1, 2, 3, 4, 5, and 6. This is sample space. Each individual events are simple events. Sample space is the collection of the simple events. And sample space is typically denoted by S. And remember, probability of the sample space is 1. So I'm just kind of, as I go through, I'm refreshing your past knowledge so that you can see it multiple times. Keep in mind. Now I define the following events: A and B, and C and D. A is the event 2, 4, and 6. B is the event 2 and 5. So if you roll a die, if the number is either 2, okay, if you roll a die and you get either 2 or 4 or 6, if any one of these three numbers show up, then event A has happened. On the other hand, if you roll the die and either 2 or 5 shows up, then event B has happened. Okay. Event A has happened or event B has happened. Make sure that you understand what the definitions of events A and B. Similarly, C and D. If you roll the die and either 3 or 6 is the outcome, then event C has happened. If you roll a die and either 1 or 4 is the outcome, then event D has happened. So when I learned these things for the first time as a student, it was kind of confusing to me to understand what does it mean for event A happening or B or C happening. It was not clear. So that's why when I'm teaching, I try to make sure that my students learn the things clearly a bit, or at least the problems I have experienced. I don't want you to experience the same problems. So I want to clarify what does it mean for certain event to happen. Now let's go ahead and show the following things, whether two events are independent or dependent, or mutually exclusive or disjoint. Oh, by the way, I forgot to define something, independent events, which technically is easy to define. Probability of an event A is the same as the probability of event A given that B has happened. If you have these conditions satisfied, events A and B are called A and B are independent. Two events are independent if probability of event A is the same as probability of event B A given that B has happened. There are two equivalent definitions here. This is one way of defining it, or you could say probability of event B is the same as the probability of B given that event A has happened. These and these are equivalent definitions. These and these are equivalent definitions. Now, what does it mean? Again, let me simplify it. What I have here is very kind of mathematical, and people might get confused by it. What it is this, very simple. It is saying that two events are independent if one happened doesn't influence the other. That means it doesn't matter whether the other one happened or didn't happen. Okay. For instance, a student X coming to the class and student Y coming to the class are independent because student X comes to the class, that probability is not influenced by student Y coming to the class or not even coming to the class. That means if John comes to the class, it's not going to be influenced by whether Jennifer comes or she doesn't come to the class. Okay, so that's what it is. In ordinary or layman's term, two events are independent if one doesn't influence the other in any way. You can think of it that way. The occurrence of one will not be influenced by the occurrence of another. Okay, like for instance, you passing the class, it doesn't have much to do with whether it's raining during the semester a lot or not. Okay, the event A is you passing the class, event B is raining a lot during the semester. The probability of event A is the same as the probability of event A given that B has happened. That means whether it rains or shines, it doesn't really matter whether you pass this class or not. Hopefully, I gave you enough information to understand what is independence, right? Anybody has any question on independence? No? All right. So remember these two equivalent definitions, probability of event A, okay? Probability of event A is the same as the probability of event A given B has happened. Probability of event B is the same as the probability of B given that A has happened. Next, let's go ahead and now do this problem. So easy one to do is the mutual exclusiveness. Two events are mutually exclusive or disjoint is if event A intersection B, the probability of this intersection is 0. Okay. If the probability of the intersection of the two events is 0, then these two events are disjoint. So let's find A intersection B first. Now you can see how the other things that you learned last week will help you solve these problems. We talked about A union B, right? We talked about A union B. We talked about A intersection B. We talked about event A and its complement, all of these things. So these things are needed for you to be able to do this problem. So A intersection B. So somebody tell me, what is A intersection B? Anybody? What is A intersection B here? Anybody? Nobody wants to volunteer? Mercedes, do you want to volunteer?
Is it it's for the dice, right? So it's like 1 and 3.
A intersection B 1 and 3?
Yeah, like it's the probability of it not happening, right?
No, first I want to find out what is A intersection B. This is my A and this is my B. What is A intersection B? Meaning I'm looking for items that are both in A and in B.
It would be just 2?
Just 2, exactly. It would be just 2. A intersection B is just 2. Now, what is the probability of A intersection B? Which is the same as the probability that 2 will show up when you roll a die, which is what? 1 out of what? 6. That is 1 out of 6. Obviously, which is not equal to 0. So that means these 2 events are not mutually exclusive. These 2 events are not mutually exclusive, or they are not disjoint. Is this clear to everyone? You need to understand these kind of things. It's very important. Again, I will be asking you these type of questions in the exam.
I have a question. Because it doesn't equal 0, it's not mutually exclusive?
Exactly, or not disjoint, yes.
So the answer has to equal 0, and then it is
Disjoint. Disjoint or mutually exclusive. Yes, okay. You're right.
Okay, thank you.
Now, while we're on the topic, now somebody tell me C intersection D, what is it?
They don't have one.
So
0.
it's going to be
0.
It's not 0. 0 is a number. It's the empty set. That means a set with nothing in it. Okay. If you say 0, what it means is that I understand what you're trying to imply. 0. It could be that you could have a set. Let's say P is a set which has 0, 2, 0, 1, and Q is a set which has 0, 1.
And that would make it. No, go ahead. 0 would be their number that they have in common. Or
exactly.
It would make it mutually
non-empty.
Exclusive. Okay, I get it.
Okay. Yeah, because this set has one item, which is 0. So it's not an empty set. Okay. Whereas this set has no item, it's an empty set. As a matter of fact, let me just be a little bit notationally clear. We don't even put the curly braces around it. We just put phi around it. Just phi, which
it has no set.
Yeah, that's the null set. So now what is the probability of C intersection D, which is the probability of the null set, which is what? By definition, the probability of the null set is always 0. So probability of C intersection D, oops, not B, but D, C intersection D is 0, which is the definition of what?
Mutually exclusive disjoint.
Mutually exclusive or disjoint. So C and D are disjoint, whereas A and B are not what? Disjoint.
Because it doesn't equal to 0.
Yep. For A and B, it was, so we found probability of A intersection B was 1/6, right? Because 2 is common between both of them.
Mhm.
So probability of getting a 2 when you roll a die is 1 out of 6, which is not 0. Therefore, it is not disjoint or not mutually exclusive.
Mhm.
So that's something you may want to keep in mind. So now we did mutual exclusiveness / disjoint for both of these problems. But how do we show whether it's independent? Remember, an event can be either independent or not independent or equivalently dependent. So if an event is not independent, by definition, it is dependent. Okay? So how do we show that two events are independent? Remember, it doesn't matter what happens, whether it rains or shines. It has no bearing on whether you pass the class or not, right?
Mhm.
So think A is the event. Let's use P. P is the event. You pass the class, okay? Q is the event.
You
It
don't
rains a lot, okay?
Mhm.
Probability of P is the same as the probability of P given Q, right? Because it really doesn't matter. It doesn't influence your chances of passing the class, whether it rains or shines. Okay, so they don't influence each other. Or you can say probability of Q, probability of raining is the same as the probability of Q given that you pass the class, right? Raining is not, the chances of raining is not influenced by whether you pass the class or not, or vice versa. So these are kind of side things. Now let's go ahead and find the A and B. I mean, probability of A must be equal to probability of A given that B has already happened. If these two are equal, then these two events are what? Independent. Now let's check it. What is the probability of event A? What is the probability that event A will happen? What is it? You're rolling a die. What is the probability that you will get either 2, 4, or 6?
1/2.
Thank you. 3 out of 6, which is what? 1/2, right?
Mhm.
So probability of event A will happen is 1/2. Now, let's try to find out this guy. Probability of A, event A, given that event B has happened. So remember now, what is given, that is something you can take for granted. You can assume that that is 100% likely to happen, okay? What is given is something that has already happened, okay? So probability of event A given that B has already happened. B happened means what? It's either 2 or what? 5, right?
Mhm.
B has happened, that you have been given that information. B has happened means what? The outcome of the rolling of a die is either 2 or it's a what? 5. Is it okay? Now, if B, you know for sure that B has happened, what are the chances that A will happen?
One-
If, yes, go ahead.
It's 1/6 because they only share 2.
Yes, half truth. Okay, you're correct, 50%. It's not 1/6, but your argument that they share 2, right? B has 2 and A has 2. So A will happen only if the 2 has shown up. Is that correct? A will happen if 2 has shown up when you roll the die. What if 5 has shown up instead? Then A has not happened, right?
Correct.
So you know for sure that B has happened. If B has happened, A will happen only if 2 shows up instead of 5. What are the chances of that happening? 1 out of what?
1/3.
1 out of
6.
6. I want a volunteer here. As many. I already have a volunteer, a couple. I want other people to participate. Brandy.
Yes.
What is your recommendation? It's 1 out of?
Six.
Ulysses, what is it? Ulysses, are you there?
Would you have to find B the same way that you found A? And then that's how you're gonna find that number? Because I kind of looked at it because there's only 2 numbers. You would do the 2 divided by 6 because there's 6 numbers. You're doing, and it would equal 1/3. No, one. So
It's gonna be 1/2, right?
Who is talking?
It's Jerry.
Jerry, okay, I'll get to you in a second. Juan Perez, what do you think? Juan Perez, Keelan, what do you think?
1 out of 6.
Okay, anybody else? One last chance.
Or would it be 1 out of 5? Or 1 out of, oh, never mind.
Okay, Brandy.
would it
All
be
right.
3?
Sorry.
Yes, go ahead. 1 out of 3?
Yeah, I'm gonna go with 1 out of 3.
All right. Okay. Plenty of chances for everybody. Now let me do the problem. So what do we know here for sure has happened in this probability? We know for sure that B has happened, right? Whatever is given to the right of the vertical line, that is something you know for sure this has happened. We know for sure that B has happened, correct?
Yes.
That means the outcome is either 2 or what?
5. Oh. Are you looking for the numbers that you have not rolled? Would it be 1, 3, 5, 4, and 6?
No.
So it'd be 1 out of 4.
No. So good try. All of these are great tries. Now you know you have to think very without any bias. You have to think without any emotions. That's when you will actually see. Okay, think logically. What has happened? B has happened. So the outcome must have to be either 2 or what? 5. The outcome has to be either 2 or 5. Now, only if 2 happens, that's when A will happen, right? So that means the chances of 2 happening out of these 2 outcomes is going to be 1 out of 2. 1 out of 2. And Jerry, I think you mentioned it's 1 out of 2, and that's the reason. You know for sure that B has already happened. That means it cannot be anything else. It cannot be 1, it cannot be 3, it cannot be 4, or it cannot be 6. None of these are possible because we were told that B has already happened. In that case, we know that it has to be either 2 or 5. What are the chances that it will be a 2 out of these 2? It's 1 out of what? 2. Now, Alicia, do you see it now?
Yes, because there's only 2 numbers there. There's only 2 chances. So it's 1 out of 2 of those numbers.
Okay. Other folks, everybody, do you see it?
Yes.
Yes.
Okay. So what is the probability of A? 1/2. What is the probability of A given B? Is also what? 1/2. Are they equal? Yes.
Yeah.
If they are equal, then these 2 events are what?
Dependent.
Independent. 2 events are independent if the probability of A is the same as the probability of A given what? B. So these 2 events are independent. Is it clear, everyone? That's the definition right here. Look. 2 events are independent if probability of A is the same as the probability of A given B, or probability of B is the same as the probability of B given A. I'm missing 2 parentheses, closing parentheses here. Make sure to add those. They are equal. So therefore, these 2 events are independent. Now, can I move on a little bit or no? Everybody okay? Any question, anybody? All right. Now I'm gonna do something else. Look, I say probability of A is the same as the probability of A given B, or I could also say it the other way, probability of B is the same as the probability of B given A. Okay, probability, just the other way. In the last example, I used this one. Probability of A is the same as the, or equal to, probability of A given what? B. I used this one. Now I want you to use the other equivalent definition. That way you will get a more solid understanding. Now, what is the probability of, I want volunteer for this one. And not the, I prefer people, all the people to participate. So please, if you're not talking, I want you to participate. Please do. Because participation helps you understand things and be more proactive, and learning takes place when you interact, not by sitting down and listening, or I don't even know whether you're listening. You might be, as far as I'm concerned, you might be on the Zoom and sleeping. So unless you participate, I don't have a way of ensuring that you are proactively engaging with the class. So please do participate. Okay. All right, so I want a volunteer. What is the probability of event B here?
2 and 5.
2 and 5? What do you mean 2 and 5?
Well, which one are you looking at? Which one are we doing?
Probability of event B.
It
If
would
you
be
roll
the
it
1/2, right?
1/2, why 1/2?
Because of the 2 numbers in B. You only have 2 numbers in there. No, it would
It would
be
be 1/3, right?
for the total number. Because
Okay.
2/6.
Remember, here you don't have anything that's given. It's just straightforward probability, right? So what is the probability that B will happen when you roll a die? That will be 2 out of 6 because there are two numbers, right? So it's going to be 2 out of 6, which is 1/3. I think, Jerry, you said 1/3, right?
Yeah.
Okay, so the probability of event B is 1/3. Now I want other volunteers. Probability of event B given, remember, given, that is for sure, 100% it has happened, that A has happened. Now we know that event A has happened. Now what is the probability that B will also happen when event A has happened? And I want a volunteer for that. Michelle Gonzalez. Michelle Gonzalez.
It'd be 1/2.
Who is talking? Alicia?
Yeah.
Okay.
Because it would be because for probability A, there's 3 numbers that you'll get. You're gonna divide it by the 6 to get the 1/2.
Okay. David Harrison, I guess, or Harrison. David.
Would it be a 1/3?
Okay. Why do you say 1/3?
So from the excuse me, from the 3 numbers that there's there, since we know that those are already happening, there would be it could only be those 3 out of the 6.
Mm-hmm.
And so from there, 3 6 is just equal. Oh, I'm sorry, it'd be 1/2.
Okay. All right. Okay, David. Araceli.
I also sort of agree with David, but I'm not sure if that's the right reasoning on why it would be 1/2.
Okay. Anybody else? Annalisa?
I'm gonna have to agree with David. 1/3.
Okay. David is popular today, yet wrong. So first of all, what do we know has happened? A has happened, right? Which means that it cannot be anything other than 2, 4, or 6, right? A will happen only if you get either 2 or 4 or 6 when you roll a die. That's when A happens. Now, if A has happened already, when will you get B also happening? If you get a 4, A has happened. Has B happened?
No.
If you get a 6, A has happened. Did B happen?
No.
But if you get a 2, A has happened. Has B happened?
Yes.
Yes. So your possibilities are these 3 numbers, and out of these 3, there is only one that's gonna ensure that B also happens, which is gonna be what? 1 out of?
2.
1 out of how many?
1. 3.
How many?
1 out of
3.
3.
1 out of 3. So this is also 1 out of 3. Are they equal? Yes. Therefore, these 2 events are independent. So that's how you should be thinking. This takes a, by the way, this is, in my opinion, probably the hardest topic in the class. Okay. There is one a bit more harder than this, but it builds onto this. If you are solid on this, then you will understand that one, which is called Bayes' theorem. But this is what Bayes' theorem is dealing with, conditional probability. So you have to think what is given. Here it is given that A has already happened, which means you got either 2 or 4 or 6. It cannot be 1, or it cannot be 5, or it cannot be 3. It cannot be 1, 5, or 3 if A has happened. This is not possible. It has to be either 2, 4, or 6. Now, if you know that it is 2, 4, or 6, what are the chances that B will also happen? Out of these 3, there is only one that's going to make B happen, which is 2, right? So your chances of B happening, given that A has already happened, is 1 out of 3, or 1/3. See, both of them are equal. Therefore, these two events are independent. This requires a bit of thinking, okay? So watch the video if you are not following 100%, and sit down and try to make some sense. Now I'm gonna do the exact same thing for C and D. We're gonna do probability of C, check whether probability of C is the same as the probability of C given D. In the second case, we're gonna do probability of D is the same as the probability of D given C. We are going to check this. Okay. Let's go ahead and do the first one. This one we're going to do. What is the probability of C? Need a volunteer. What is the probability that you will get a 3 or 6 when you roll a die? That means C will happen.
1/3.
1/3, exactly, you're right. It's 1/3, which is what? Why is it 1/3? Because there are 2 items here. So 2 out of 6, which is 1/3. So this is 1/3. Now let's do probability of C given that D has happened. D has happened means it's either 1 or what?
4.
4. Now, if we know for sure that it is 1 or 4, now will C happen in that case ever?
No.
No, because if it is 1 and 4, we know for sure C cannot happen. Well, because C has 6 and 3, right?
Yes.
C cannot happen. So this is going to be what? 0 out of 2, correct?
Yes.
Which is just 0. So this number is 0. Are they equal?
No.
No. Therefore, these two events are what? If it is not equal, then these two events are not independent, or equivalently, they are what? Dependent. Equivalently, they are dependent. Remember, they have to be equal for them to be independent. Now let's do the same thing here. What is the probability of D? Now I'm using this guy. Probability of D. Can somebody tell me what is the probability of D? Again, it's 2 out of what?
6.
6, which
So
is
1/3.
1/3. So this is 1/3. And now probability of D, given that C has happened. Probability
0.
of D, given that C has happened. If C has happened, we know it's either 3 or 6. Can D happen?
No.
No, because it's 0 out of what? 2 or
2.
0. So this is 0, right? So this is not equal. Do you see? It doesn't matter which way you do it. You'll always get the same conclusion. You may get different numbers, but the conclusion is the Same. So this is very important for you to understand conditional probability. See, these conditional probabilities are all over in your life. You just don't think about it. So what is the probability that you'll get in an accident? Let's say A is the event, you get in an accident. Hopefully it doesn't happen. What is the probability that you'll get in an accident given that you're tired? T is the event that you're tired. See? What is the probability that you'll get in an accident given that you are tired? Or what is the probability that you'll get a ticket? T is the event for ticket. What is the probability that you'll get a ticket given that S is the event that you're speeding over 100 miles? Do you see how conditional probability changes things? Now, let's define something politically I don't use politically incorrect. I'd call it facts. What is the probability that you will be successful as an individual in this country? What is the probability that you will be successful in this country given that you are black? What is the probability that you will be successful in this country given that you are what? White. These are real problems. These are real problems. What is the probability that you will be successful in this country given that you don't have legal status? You're a dreamer student. You know what dreamer students are? Students who came here young and they don't have legal papers. So conditional probability is everywhere. This life is not deterministic. It's uncertain. It has a lot of randomness or uncertainty associated with it. And we don't think about it. We don't think of math being useful really in real life, but it is useful. These are all real world problems. You may want to know what is the probability that you'll be successful in this country given that you are black? What is the probability that you'll be successful in this country given that you're white? Or what is the probability that you'll be successful in this country given that you are a dreamer student? And these probabilities are not equal. I'm not saying one is more or less or whatever. I'm saying they're not equal. And on the other hand, what is the probability that you'll get in an accident given that you are tired? Or what is the probability that you'll get a ticket given that you are speeding? These are problems that you deal with every single day. Or what is the probability that a mother will give birth to a normal child, okay, a normal baby? Or is the probability that mother will give birth to a normal baby given that the mother is alcoholic? These are all real world problems that impact your life in a significantly meaningful way. And yet we don't think of it that way, but we could do it. The best example is, and my favorite example is the Gmail, okay? There are billions and billions of emails going around, multiple billions of emails going around the world in Gmail every single day, right? Imagine if they have to physically employ people to separate the good emails from the not good emails or promotions or other sales emails. They would be facing significant financial challenge. It's not possible, but using conditional probability, okay, and using a little bit of AI, you can isolate these emails in the matter of seconds, not even seconds, less than a second. You can identify it, and you don't have to employ humans to do it. Then another good example would be Amazon, right? Amazon, when you buy something, you go to Amazon.com and you type in shoes, okay? Or you type in, I don't know, soccer ball, okay? Right away, it will give you information about soccer ball, and at the bottom, you'll see a bunch of related items. Somebody might want boots, somebody might want socks, somebody might want soccer gears, okay? all these things. Do you think humans are doing it? Absolutely not. They are using conditional probability and AI, a little bit of. If somebody likes soccer, they might be interested in what? Interested in
Soccer
shoes.
player.
Yeah. So probability of liking shoes, given that somebody likes soccer, let's say a C. Okay. Probability of somebody liking soccer shoes, given that somebody likes soccer. C is the event that somebody likes soccer. And S is the event that somebody likes soccer shoes. So these are very, very related. And this is like something you use. I find conditional probability amazing thing. And it has so much application. It's crazy. Now, let's move on. I think, gosh, we should take a break. I don't have much time. Can I go continue instead of taking a break and let you guys go a little early? Is it okay? Yeah?
Yes.
Yeah.
Okay, all right, let's continue and I'll let you go a little early. All right. So, oh, we are at Bayes' theorem. All right. I may not have enough time to finish Bayes' theorem today, but I will at least start it. Okay, I will be using this definition. Think of probability of A intersection B, which is the same as the probability of A times the probability of A, given that B has happened. Okay, I'm going to take the background off. Also, probability of A intersection B is equal to the same thing, equivalent definition, probability of B times the probability of B given that A has happened. Can I say that? This is just the way we define A and B. There is nothing magical. This is just what we call it is. Okay, the same thing. Like your parents named you John. Okay, that's it. Probability of A intersection B is probability of A times probability of A given B. Probability of A intersection B is the same as probability of B times probability of B given A. All right, now think these two are the same thing, right? These two are the same thing. Then it must be the case this is the same as this, which is to say probability of A times the probability of A given B is equal to probability of B times the probability of B given A. Is everybody with me on board on this conclusion? I'm saying A is equal to B, and I'm also saying A is equal to also C. From this, I can conclude that B must be equal to what? C, right? I'm saying A is equal to B, and also A is equal to C. From this, I conclude that B must be equal to C. So I'm saying that this is equal to this, and this is equal to this, but these are the same thing, right? Then this must be equal to this. That's exactly what I have here. Now, assuming that P of A is not equal to 0, I divide both sides by P of A. This and this, I cancel this. So that gives me probability of A given B is equal to probability of B given A, I'm writing this one first, times the probability of B, all of it divided by the probability of A. And this, by the way, is called Bayes' theorem. This is called Bayes' theorem. Now, Bayes' theorem is basically what is being used, okay? In the email case, we talked about, how big corporations separate their important emails from not so important emails. This is what they use. They use Bayes' theorem. Of course, it's kind of like the example I'm giving is a very simplified example. This is the theory that they use, but in real world implementation of it is extremely complicated and a lot of different things. And the model that they create, it has to be pretty much always improved or always modified or changed in such a way so that it changes, right? Remember, back in the days, you guys may or may not remember when emails came in, people used to read emails, even if it was from somebody else. They would think it's so important. I remember those days when we would look at emails, every single email, thinking that it's important, but people took advantage of us, people, those who are in sales in those days, by very easily, because people are not used to emails so much. But as time goes on, people become smarter with this, and so does those people who create spams, okay, who are advertising or marketing. They became smarter too. Now they have become more creative. So your Google model or your Microsoft model has to adjust with the changing strategies, how people change their strategies. So the models must have to be improved. The models constantly learning. By the way, when I say models, I mean artificial intelligence models, just to be clear. You guys, this is kind of not related. I mean, not the kind of topic we'll be talking in this class. Is a bit more advanced. But it is extremely related to this conditional probability and Bayes' theorem. So I like to bring it in. Now, equivalently, by the way, what if I took this guy again, probability of A times probability of A given B is equal to probability of B times the probability of B given A. This time, instead of dividing by probability of A, I'm going to divide both sides probability of B. Probability of B. Now look, this and this cancel out, and I can write this one on the left, so it doesn't really matter. Probability of B given A is equal to this one. Probability of A given B times the probability of A, all of it divided by probability of B. Now this is the equivalent definition. The difference between the two is this. This one finds probability of A given B. This one finds just the opposite, probability of B given A. Okay. You can use, this is just a labeling thing. It's not really event A. Some event, I can label it A or I could label it B. So it really doesn't matter if you switch it. The way I remember this thing is this. So probability of A given B, to find the formula, just switch it. So probability of B given A. Whatever is here, just switch it here. So this is A given B, switch it. Now multiply it by probability of whatever is not given here, B. Oops, not, sorry. What did I do? Okay, yeah. Multiply it by whatever is not given. Then divide it by probability of event A. Okay, that's what it is. There is a parenthesis here. Now let me bring this EU. Doesn't look clean. Probability of A given B is equal to probability of B given A times probability of A divided by. Did I make a mistake? I'm sorry, I may have made a mistake. Hold on, just give me 1 second. Let me just check something. Did I make a mistake in deriving it? Probability of A, so probability of A given B, probability of A given B times probability of A, probability of B given A times probability of B. Okay, now divided by probability of A, the probability of A given B. What did I do? I may have made a mistake in deriving it. Give me just 1 second. I just have made a mistake. That's why it looks weird to me. I'll tell you what the mistake is. Probability of A intersection B is the probability of A times the probability of B given that A has happened. Probability of A intersection B is probability of B times the probability of A given that B has happened. So I made a mistake. Sorry about this, guys. Let me just fix it. That means it's gonna take a little bit more time again. It's the same concept, by the way. I'll just do it for you so that you can look at it. So probability of A intersection B is equal to probability of A times the probability of B, okay? Given that A has happened. So I made the mistake that I put A here and given B. So again, probability of A intersection B is probability of A times the probability of the event B given that A has happened, and also probability of A intersection B is equal to probability of B times the probability of A given that B has happened. Now, these and these are the same, then this must be equal to this. So I'm going to write it out. Probability of B times the probability of A given B, which is this guy, must be equal to probability of A. So this guy I'm writing times the probability of B given A. Now, assuming that probability of B is not 0, I divide both sides by probability of B. Probability of B. This and this cancel out. That gives you probability of A given B, which is this, is equal to probability of B given A, probability of B given A times the probability of A, all of it divided by probability of B. Okay, this is the formula. Now, how do I remember this? Is this probability of A given B, probability of A given B, okay? This one. Now, in the right side, just switch it, probability of B given A, times whatever is given, the probability of the whatever is given for this one. Then divide it all by whatever is given here, probability of B. Now, if I switch it, let's say I write it as probability of B given A, look, it's just the opposite, right? Now I'm going to switch it here. This is going to be probability of A given B times the probability of whatever is given, which is B. So probability of B, all of it divided by whatever is given on the left-hand side, probability of A. And that's what it is. These two are equivalent definitions. Now we are going to do probability, conditional probability or Bayes theorem problems. So this is the derivation of the formula, which we call Bayes theorem, by the way, B-A-Y-E-S, Bayes. This is how you spell it. It's not B-A-Y-S. That's not the one. This is the one. Bayes theorem. This is called Bayes theorem. Now, any question on this, anybody, before I move on and do a problem? Then you guys get to go. This topic is the hardest topic, and hopefully it won't be too bad. You may have to see it a couple of times, so please be patient and watch the video a couple of times, and I'll talk about it even in the next class. Okay, not only this class, I'll talk about it in the next class as well. All right, so let's do a problem using Bayes' theorem. It's a traveling salesman. This is a problem I have to give credit to Mr. or Mrs. I don't know, Krakoska. Yeah, credit to Krakoska, Introductory Statistics. That's where I got the problem. So I took it from there. A traveling salesperson stays at hotels A, B, and C 50%, 30%, and 20% of the times respectively. So a traveling salesman goes to a city and they have 3 hotels, A, B, and C. He stays or she stays at hotel A 50% of the times, hotel B 30% of the times, and hotel C 20% of the times respectively. When he checks in, he has a problem with reservation 5% of the times, 10% of the times, and 15% of the times with the hotels A, B, and C respectively. A traveling salesperson stays at 3 hotels, 50, 30, and 20% of the times respectively. And when he checks in, he has problems with hotel A 5% of the times, right? 5% of the times. He has problem with hotel B 10% of the times. He has problem with hotel C 15% of the times. Okay. Find the probability that salesperson stays at hotel A and has problem with the reservation. So let's say I define A is the event that stays at hotel A. R is the event has reservation problem. Okay. So we want to find out the probability that the person stays at hotel A and has reservation problem. So we are looking for probability of A and R. Okay. So according to the definition, we could do probability of A, okay, times the probability of R, given that the person stays at hotel A. That's one route. Or we could say probability of reservation times the probability of staying at hotel A, given that there is a reservation problem. Both are equivalent definitions, okay? Probability of A and R. I could go probability of A times probability of R given A, or maybe I can write it A, probability of A and R is equal to probability of R times the probability of A given R. So let me use a different color. So this is one definition, and that's another definition. Now, if you go this route, you will get stuck.
Professor,
Yes.
for that second one, isn't it supposed to be P is equivalent, is R, is it P apostrophe, shoot, I got P, R, U, what is that little sign again in the middle? Sorry.
Which one? This one,
Union?
that's equal to.
Union. So is it P, R, union, A?
No, intersection.
No, intersection, sorry.
Yeah, go ahead.
For the second one, I think you got it mixed up because then it would equal P times R equals probability of A over R? Because the first one, you already have the P. Oh, no, never mind. I'm sorry. I'm so sorry. Sorry.
No, it's okay. It's okay to make mistakes. Okay, I make mistakes too. And I have been doing it for many years. These probability concepts could be a little confusing. It's good to make mistakes. It's good to get confused. Okay, so learn this. You reminded me of a story. There was a guy, very smart guy, smart physicist. He actually won the Nobel Prize in physics. His name is Richard Feynman. Okay, Richard Feynman. He got Nobel Prize in physics for his work on quantum physics. So he once said the following. He said that, you know, people, those who study quantum physics, and if they are not confused or puzzled by it, okay, confused and puzzled by it, they really don't understand quantum physics. You just reminded me of that quote. You know, this probability stuff is confusing. Trust me. Even after teaching it for many years, I find sometimes I get confused. And inadvertently, I make mistakes too. Like very recently, like a few minutes ago, I made a mistake inadvertently. So it happens, so no worries. All right, so it's the same thing, by the way. Both of these are the same definitions. So now if you go this route, you don't know what is the probability of having a reservation problem. Okay? You don't know. So we are gonna use this. What is the probability that the person stays at hotel A, which is 50% of the times, right? Or 0.5 times. What is the probability that the person will have reservation problem? Probability of having a reservation problem given that the person stays at hotel A. That also is given, which is 5% of the times. So it's going to be 0.05. So 0.05 times 0.5 is going to be 0.025. So this is the probability that the person stays at hotel A and has reservation problem. This is the probability. Now, the next one is this. The next part of the problem, find the probability. So this one is slightly different. Find the probability that the salesperson has problem with the reservation. So that means they're asking you to find the probability of R. That's what they're looking for. Find the probability that the salesperson has problem with the reservation. Now, here you have to think, it's different than this. Here, find the probability that the salesperson stays at hotel A and has problem with the reservation. So that means we are looking for probability of A and R, or equivalently, you could say probability of R and A. It doesn't matter. However, here, this is a general reservation problem. This is a specific reservation problem associated with A, whereas this is general reservation problem. Now, you can have reservation problem if you stay at hotel A. You can have reservation problem if you stay at hotel B. You can have reservation problem if you stay at hotel C. And that's all the possibilities. So this is the same as probability of staying at hotel A and having reservation problem plus the probability of staying at hotel B and having a reservation problem plus the probability of staying at hotel C and having a reservation problem. That's what it is. So this is the general reservation problem. That's why we were getting stuck the other time. We didn't know this. Now this part, probability of A and R, we found it 0.025. So we are going to write 0.025. This is this part. Now, what is the probability of B and R? probability of B and R, which is the probability of staying at hotel B times the probability of having a reservation problem given that you stay at hotel B. The probability of staying at hotel B is 30% or 0.3 times the probability of having reservation problem given that you stay at hotel B is 10% is given here. So 0.10, which is 0.03. So this is plus 0.03. Now, similarly for C, probability of C and R is equal to probability of C times probability of R given C. What is the probability that someone stays at hotel C, which is 30% or 0.3 times? What is the probability of having a reservation problem if you stay at hotel C, which is 0.15 or 15% or 0.15, which is 0.045. So probability of C and R is 0.045. Yes, please.
The probability of staying over at Hotel C is 20%.
Oh, is it 20%?
Yeah.
Did I make it?
So it would be.
So thank you.
Mhm.
This should be 0.2. So it's going to be 0.03, right?
Yeah.
Thank you. 0.03. Let's clean it up. 0.03. 0.03. Perfect. Now, if I add all these three numbers, I'm going to get probability of having a reservation problem. 0.03 plus 0.03 is 0.06, right? 0.06 plus 0.025 is 0.085. Did I do it right? Can somebody check it for me, please? Oh, I have a calculator. I can quickly
Yeah,
check
you
it.
did it right.
0.03 times 2 plus 0.025. Yeah, 0.085. So overall reservation problem, overall probability of having a reservation problem is about 8.5%. Whereas if you stayed at hotel A, the reservation overall reservation problem associated with hotel A and you stay at hotel A is 2.5%. Okay, so this is something, is a bit of a thinker. Okay, so you have to kind of like look at these problems a couple of times before you get a feel for it. I think I will stop here for the day because there is a third part to the problem, this one where we use the Bayes theorem. I'll give you a hint and then you can go ahead and work on it. I'm going to start from here next time. Given there is a reservation problem, given, read it carefully, given that there is a reservation problem, that means R is given, then find the probability that the salesperson stays at hotel A. So what they are asking you is probability of staying at hotel A given that there was a reservation problem. Now this is Bayes theorem, which is going to be probability of R given A. See, you switch it, you switch this one, times probability of whatever is given on the right side, which is A, all of it divided by probability of reservation, or R. Actually, I can just finish it. So probability of R, we just found it, is 0.085. We just found it. Probability that someone stays at hotel A is is it 50% of the times? Is 0.5, I think.
Yeah.
Hold on. It is 0.5. Now, probability of reservation, probability of R given A, okay? Probability that you will have a reservation problem given that you stayed at hotel A, right? So which is, I think, what number was it?
I mean 0.025.
No, that's probability of staying at hotel
Hotel
A and so probability of a reservation problem, given that you have made the reservation at hotel A, is actually 5%. Probability that you will have a reservation problem, given that you made the reservation with hotel A, is 5% or 0.05. Okay, so what does it come out to be? 0.05 times 0.5 divided by 0.085, which is 29.41. This is 0.2941, or which is approximately 29.41% chance that you will stay at hotel A, given that there was a reservation problem. And that's all it is to this problem. I kind of covered a lot of materials today, so you may want to look at this video a couple of times and get confused, which is good. And we will go over the same things again on Monday. Please spend the weekend looking at it a couple of times. It's okay to get confused. It's okay to make mistakes, okay? Just watch the video, try the problems, and that's when you'll start to get a feel for it and you'll start to make mistakes. And then on Monday, I'll do it again so that you can go ahead and get a better understanding and clarify any questions that you may have. All right, folks, thank you so very much. You have a wonderful weekend. And also I have extended the deadline for the last homework. Okay, so you have more time to work on it, and I'm gonna go ahead and put another homework on Bayes theorem online. I'll do it today so that you can work on it over the weekend and bring your questions, okay? And if you get confused, don't give up. Don't be shy in asking questions. Don't get frustrated and give up. These topics are a bit harder than usual. So just hang in there. I'm here to help you. Okay? Just hang in there. I'm here to help you. Just my expectation from you is that you just try these problems, look at the videos, and try to understand it. If you get it, great. If you don't get it, that's also great. You just come to the class and ask me, and I will help you. All right, thank you, and have a wonderful weekend. Stay safe, stay healthy, okay? Take care.
Thank you, Professor.
Thank you.
Thank you.